Started.
You forget.
Just to point at this, maybe it might be.
There's a sticker.
And to move this, I'll just use
Yeah,
that's fine. That's perfect.
Wait, after that, we have.
Yeah,
right?
yeah.
Okay, so maybe you can start. Welcome everybody. It's great to have Venkat back. So things are normal now. Right? I hope it is more often. Please,
Thanks a lot, Vivek. It's fantastic to be back here. It's 2.5 years since coming to TFR, I think, roughly speaking. And I used to be a very frequent visitor, more than once a year, probably twice, 3 times a year. So it's great to see everybody looking good and healthy. So let's hope that it doesn't get worse. So this is a work on, actually, the way I'm going to present it is basically going to be work on data compression and specifically on lossless compression. But I want to emphasize that the way you want to think about this work is as a paradigm for doing estimation problems or data analysis. So even though I'm presenting it as work on compression, the larger message is that it could be applied to various other kinds of estimation problems and so on. And I'll try to make that just apparent as we go along. This is joint work with Prasad, and I'm Prasad Santhanam at the University of Hawaii, and Wojciech, who's Wojciech Spankowski at Purdue University. And the paper has already appeared in Journal of Machine Learning Research, JMLR, this year, 2022. So you can, there are a lot of details, which if you're interested in, you can go to the paper. So first of all, what is lossless compression? It's widely used, as many of you might know. Every time you're getting an image on your cell phone, or you're sending an email or storing something on your computer, typically compression is used in order to save resources, to reduce the size of what you send in bits. So basically, the idea is that the idea of compression goes long back. So if you think of your image or your audio clip or your text or something as being some symbol from some big set. And each symbol, you might have a model that says that symbol X is seen with probability P of X. So basic idea behind compression is to try to use shorter representations for more probable symbols. So then on the average, there is an expectation you probably are doing a pretty good job. So this early example, for instance, is Morse code. This is what Morse code looks like for the English alphabet, including some non-alphabet symbols, numbers, etc. So, for instance, as everybody probably knows, E is probably the most common letter in the English alphabet, so it gets a very short representation. That's basically the idea of compression, of lossless compression. So, throughout this talk, I'm going to assume that the alphabet from which we draw our symbols is going to be countable, so either countably infinite or finite. So we might as well enumerate it with the natural numbers. So our alphabet throughout the talk is just going to be the natural numbers. But if there are any questions, please feel free to stop me. It's a fairly slow-paced talk, I think, related to most talks. But okay, so what is a compression map? It's you can think of it formally as a function from the symbol alphabet to bit strings, non-empty bit strings. This traditional computer science notation for the set of non-empty bit strings other than the empty string. Now, typically you might see actually sequences of symbols. For instance, you might see a sequence of images, or many of the standards that are used for transmitting video, etc., send sequences of frames. So you want to have the property that you know when one frame has ended and the other one is starting. One way to achieve that is through what's called the prefix free condition. So you insist that this mapping phi has a property that if you have two different symbols, then neither of them is a prefix as a bit string of the other one. And this then implies an inequality, for which I have a picture in a minute. It says that if you look at the sum over the symbols, remember symbols are drawn from natural numbers, 2 to the minus the length of the bit string phi of x, then that has to be less than or equal to 1. So you can think of the problem, roughly speaking, as of trying to minimize the expected length subject to this condition. So this Crafts inequality is quite easy to understand. Typically, if you're in a course in information theory, you might see something like this on the first day itself. The dark dots represent the bit strings that are actually being used. So you think of this as a standard binary tree. That's a root. You either 1 or 0 going up or down. So if you think about the strings that you actually use at any given depth, and you associate, say, depth 2, you associate these with weights 2 to the minus 2, and depth 3 with weights 2 to the minus 3. As long as no black dot is on a path from the root to another black dot, you pull back all the weights, and that's how you prove Crafts inequality. So to kind of understand the problem of trying to do optimal compression, you can consider relaxation, the traditional thing to do in computer science. So you will relax the optimization problem by allowing the lengths to be arbitrary non-negative real numbers. Once you do that, you realize that you might as well make Crafts inequality into an equality, because you have nothing to gain by using longer lengths. So you might as well push the inequality up to an equality. And the non-negativity condition also is sort of automatic, because these things can only add up to 1. So you don't have to explicitly write that down either. So you're led to look at this Lagrangian. This is a Lagrange multiplier. This is your objective. And now that's an equality constraint. So to solve this problem, you would differentiate in each of the variables. The variables are now these real variables, L of phi of x.
So what's the input? You're given the p of x as a table, or?
So I mean, right now this is not necessarily a computational viewpoint. It's just a question of figuring out what the best is that you can do. Right? So in case
even if not computational, what is the as a function? It takes p of x and is going to spit out.
Yeah. So the object that is fixed is the probability distribution p of x, which for the moment is assumed to be known. The variables that you're trying to determine in the optimization problem are the L of phi of x. And this constraint, which was an inequality, is now an equality. So this is Lagrangian approach. You differentiate in these variables, and you get p of x plus lambda times this log e to be 0 for all x. This tells you that the optimal L's are basically log of 1 over p of x. And so you realize that the idealized optimal value of the objective is basically the Shannon entropy. This is actually one way to sort of make the Shannon entropy show up naturally, so to speak. Right? People often in information theory courses might do that in the first couple of lectures. So this is the idealized optimal value. So now any specific compression scheme, what you might be interested in then is how far away it is from this idealized value. So that would be its own what it achieves. So the phi now is our compression scheme. This is the expected value of the number of bits. I mean, so it's the performance of the compression scheme. This is, so to speak, the ideal, although that allowed for these to be real numbers. Remember, there was a minus sign, so two minuses make a plus. So this difference, this quantity is typically called in the theory of data compression the redundancy of the compression scheme, which is how far away it is from the optimal, so to speak. So everything I've said up to this point is based on the sort of mindset that you kind of know the distribution with which the symbols are arriving, but you might not know that. Right? You have a data stream being thrown at you. And now what you might then ask yourself is, this is a question of what's called universal compression, so to speak. So you might want to ask yourself how you can come up with a good compression scheme that is good, irrespective of what the underlying symbol distribution is, as long as you have some idea of what class of distributions that symbol distribution might be coming from. So we are not going to start talking about model classes. In fact, that's what our focus will be throughout the rest of the talk. So a model class for us now is going to be a subset of probability distributions on the natural numbers. So now the setup is that you're going to see the symbol, and it's drawn with a law which you kind of know comes from P. So I put no in quotation marks because it's really a modeling assumption. So you kind of believe that it's coming from this model class P. But you don't know which specific model within the model class is governing the sample. Now, if you want to evaluate a specific compression scheme, a natural way to do that is to think about the worst possible redundancy over the models in the model class and to try to choose a compression scheme that is the best. So you're now faced with this min-max problem.
So one thing is the little piece. Does it remain fixed too long?
Yeah, so that's what we're going to assume. We're going to assume, in fact, that we have a model class which is determined by this marginal distribution, and the symbols are IID with that model.
Is it allowed to even?
No, we are going to assume that it's the same.
There is no hypothetical thing.
No such thing. I mean, I'm just doing baby stuff. All these other things have been studied, in fact, model classes that are ergodic and blah, blah.
That's why I'm asking the next question. How are you doing the supreme?
Yeah.
Why would we not learn as you go along? Because little bit possibility is learnable, in which case you don't have to do this.
No, so if you're trying to evaluate a specific compression scheme, which in this case is defined at the moment as just a mapping from symbols to bit strings, well then you know for any given P, this is its performance, and then you do the super. So the kinds of things you're suggesting are going to come up in a minute, which is naturally you don't want to necessarily do it just symbol by symbol and so on. So I mean, we're going to get there, and so just setting the stage for. Actually, this is not even, as I said in the beginning of the talk, this is not even the main point. I'm just using the compression area, which we analyze in depth, to propose a philosophy for estimation problems, and that's really the point you want to take away later. So we haven't got to that yet, yeah. But very valid point here. So at the moment, that's so we're left now to deal with this min-max problem, which is to once we're dealing with the model class scenario, to try to minimize over compression schemes the worst case redundancy. So this is the first look at the redundancy. So this is still a bit clunky because it involves this mapping from symbols to probability to bit strings. So now you want to realize one more thing, because everybody in information theory knows all this very well, which is that if you're given, so think about some other probability distribution on the set of symbols, which for us is the natural numbers, call it Q. You can take the ceiling of the log to the base 2 of 1 over Q of x, that gives you now integers, natural numbers, and write L of x for that. If you compute the sum of 2 to the minus L of x, it's exactly equal to this. So the ceiling is larger than equal to the thing inside, so you get this bound. So you suddenly realize that these numbers actually satisfy graphs of equality. So it's rather easy to see by running that tree picture in reverse that this implies that there exists a compression scheme whose lengths are precisely these lengths. It's not hard to see. Now, if you look at the redundancy associated with this particular compression scheme, which is associated to a Q, and now from this point onwards, my logarithms for the rest of the talk are going to be the natural base. I want to drop the log to the base to B. You realize that the redundancy is basically lower bounded by a standard quantity, which is the relative entropy, because the ceiling is bigger than or equal to log 1 over Q of x. And it's less than or equal to 1 plus the relative entropy, because these things can go up at most 1, and sum of P of x is equal to 1. So rather than dealing with this clunky business about functions from symbols to bit strings, you might just define the redundancy of an underlying probability distribution Q, so to speak. And you might pose the problem of finding the best, so to speak, compression scheme over a model class as this min-max problem, where you're trying to find the best Q, which has the best worst case performance in terms of this proxy for the redundancy. So that's really how people discuss redundancy in compression. Again, feel free to ask questions. So this is how you'll see in the literature redundancy. People just sort of define it like this, but this is where it comes from. And now we get to the kinds of things that Rahul was suggesting. So of course, typically what people do is they compress in blocks. And here I'm making the definitions for arbitrary model classes of probability measures on sequences of symbols. But that doesn't mean we're going to deal with that in this talk. The talk is entirely going to be for IID model classes. So a model class for us is equivalent to a set of probability distributions on the set of symbols. So if you're now willing to do your compression at the level of blocks, so you take a block of n symbols and then you map it to bit strings with a prefix free condition, etc. Then the redundancy quantity that you would be interested in for a given model class would be this thing, which is the infimum over all q. Really, you just want probability distributions on strings of length n of symbols, but you might as well take it to be on measures because you can just look at the first n symbol. And supremum over the distribution of the model class. dnrq here is the is basically drq at the level of blocks of length n. So this quantity is called the n-letter redundancy. For n equal to 1, it's called the single letter redundancy. And if you sort of now willing to go all the way to asymptotics, then it's natural to think about the redundancy on a per letter basis. So you take the n-letter redundancy divided by n, and take the lim sup of that as n goes to infinity, and that's what's called the asymptotic per symbol redundancy of the model class. It's all standard terminology in the compression literature. Yes.
So here we know that Q should also be from lambda. If we know that the choice of R is from lambda, we can always choose Q to also be from lambda.
No, that's not necessarily true. Q is just the thing that actually describes the compression. Q is like a proxy for the feed. So it is so really the role that Q is playing here is something where a Q is replaced by a bit string of length, ceiling of log of 1 over Q. So that generally has very little to do with the lambda.
Yeah, it's a scheme for that. It's a compression scheme for that specific.
It's a compression scheme for the class lambda, but the measure that represents the compression scheme has nothing to do with the model classes. I mean, the model class might be just one model, right? And the compression scheme might have nothing to do with it. If you knew what the distribution was, the model class would have just one point in it, but no reason why the compression scheme you use ends up looking like that a priori. I mean, I think intuitively you might start to think that it should, because the entropy is the right thing, right? So there's something to your intuition about it, but that's not assumed. I think one way to see that you wouldn't expect that at an intuitive level would be to think about model classes that might have, say, 2 points which are far away. The Q might want to be somehow good for both of them, and it only has to fall in the middle. So that's better answer to your question. So anyway, so this standard terminology, asymptotic per symbol redundancy. Now, as defined, what we do is we fix n. We study the n-letter redundancy on a per symbol basis, and then we take the lim sup. But it turns out sort of magically that you can actually interchange the lim sup and the inf, and that's a very useful thing to know. And we use that in our paper. I'm not sure that it's necessary for me to say that here because I'm not going to give you too many proofs. But I think it's a very central trick in this area, which is worth mentioning at least. And the basic idea is that you can somehow replace the essentially, fix an epsilon bigger than 0, which is eventually going to go to 0. For each n, you can find some qn, which is, so to speak, epsilon optimal for that block length n. And then you can mix those such epsilon optimal qn's with some weighting factors which add up to 1. And think of this one single distribution. Now, when you try to compute redundancies with respect to one single distribution, if you just use one of these factors, say the one for block length n, you'll get an even bigger number because the q comes in the denominator. But the amount of loss that you get, because the log is basically like log of n times n plus 1, when you divide by n, that goes to 0. So it's like there's enough juice of each of these qn parts in this q that it picks up the correct asymptotics. This is an important technical thing to do. You can kind of interchange the lim sup. Okay, all this is just setting the stage. So now I want to sort of get to what the main philosophical thrust of what we did is. So people are trying to study how to come up with good compression schemes without knowledge of the underlying model class, of the underlying model in the model class. And it has generally been historically the case for the several decades that data compression has been studied, that there's a kind of dichotomy that people focus on about whether, I mean, what is possible for a given model class. So certain model classes are called strongly compressible. And basically a model class is called strongly compressible if the entire model class has got vanishing asymptotic per symbol redundancy. So what this basically means operationally, if a model class has this property, is that if you give me some fixed delta, which is like a target within which you want to get the redundancy over the entire model class down to less than delta, then you can find a fixed block length n depending on delta, and the fixed compression scheme working at that block length, so that irrespective of what the model is within the model class, the per symbol redundancy will be at most delta. So there's some kind of uniform notion over the entire model class. And I mean, this you can see comes from the definition. Actually, I have one more slide making that clear. So let me show that. So basically, the operational view is that for all n there exists a qn such that this thing goes to 0, and it's sort of equivalent to this. I'm not sure the slide is that important, but just pointing out that it's this. But the point is that the philosophical point is in the last slide here. So if a model class is strongly compressible, that's great, because now you have this kind of uniform guarantee for the entire model class. For a given delta, you know how big you want to make n, so that you can get performance within delta. But for a model class to actually be strongly compressible is pretty hard, right? So you don't really have that much modeling flexibility that you can't really work with very rich model classes. So the other extreme that people work with, typically in the literature, historically for many years, has been the notion of weakly compressible model classes. Again, we're focusing toward this talk just on IID model classes. All this has been done much more generally in the literature. So model classes can be weakly compressible if there exists a compression scheme, which in effect boils down to, as we discussed because of that trick, to a measure on sequences of symbols, such that for every model with finite entropy, this is technically necessary to assume this, we have vanishing asymptotic per symbol redundancy with respect to Q, namely that when we use this Q as our proxy for a compression scheme, we have vanishing asymptotic per symbol redundancy for each model in the model class. What that means is that irrespective of what the model is within the model class that is driving the data, if you wait long enough, you'll get the per symbol redundancy to be as small as you like. But you don't know when that's going to happen. So this is like a pointwise notion over the model class of being able to compress well. Whereas the strong compressibility was a uniform notion. So operationally using the fixed block length schemes that are defined by this one Q. This Q basically boils down to a bunch of QNs because of that trick. So just we'll talk about this one Q. You'll be able to give asymptotically vanishing per symbol redundancy, whatever the model is enforced within the model class. And the reason for this finite entropy at an intuitive level is that if the model itself had infinite entropy, what's the point of talking about redundancy? You're just talking about something which is because the entropy is infinite, so infinity bigger than infinity. So that's, but mathematically it's kind of, you need to have this when you try to prove something. So this is the traditional dichotomy, and the problem. So here the point is, this is great because now you can allow for much richer model classes. But the bad news, as you notice immediately, is that the convergence need not be uniform over the models in the model class. So if you are at any fixed block length, all we have in front of us is data. We don't really know what model is enforced. So we don't really know how well we are doing. We know that if we wait long enough, we'll be doing well, but are we doing well right now? And this is precisely the line of issue. This issue is precisely what our line of work addresses. Of course, this is not rocket science to realize that this is an issue. So there are many other ways that people have tried to address this in the machine learning literature. Some ideas like luckiness, things like that, and so on. So it's related to other kinds of work in the machine learning literature. With our particular take on this. And in this context of compressible compression, which I'm talking about in this, which we're talking about in this work, what we propose is a new concept, which we call data-derived decompressibility. And a model class is said to be data-derived decompressible if certain things hold. I'm going to define that in the next couple of slides. And it turns out that every strongly compressible model class is data-derived decompressible, but there are data-derived decompressible model classes that are not strongly compressible. So every, and we just call this DWC because it's a big mouthful. So every DWC model class is weakly compressible, but there are weakly compressible classes that are not DWC. But if you have a model class that is DWC, then you are also able to give a guarantee at specific times that you're doing at least delta well. That was the motivation. And now the main philosophical point. This because doing this for compression, but you can imagine this paradigm as being relevant to any estimation scenario that you're working with. If you're dealing with an estimation scenario where you have something which is roughly speaking non-parametric in terms of the driving variables are drawn from some model class of distributions. There's your natural instincts from the literature is to think about the uniform versus pointwise dichotomy. But you can use the approach that I'm going to describe now, having a data-derived object in between the uniform and the pointwise, and thereby you can get finite time guarantees. So that's the philosophical point. We already have done this earlier, actually, Prasad and myself, in work that we talked about as being model agnostic insurance, which I'm going to mention again here, which is related to, which can also in the probabilistic language, it can be treated as what's called a tail domination problem. I'll mention that earlier. So we've already worked that out in that context, and there are many other contexts that we would like to work this out on, and if you're interested, you could. What's going on? Is the free?
Is it going to end?
Sorry?
No, the message was there.
Message said that in 10 minutes something is going to happen. Okay. Oh, it might be something to do with the zooming with the
nothing changed yesterday. So, new month.
You just restart the same meeting.
No. The streaming recording out into Zoom.
Hi, can you give some examples of compressible and decompressible?
Yeah. All that is coming. I mean, all this is going to be fleshed out. We have tons of examples in the paper, and in fact, we constructed specific examples to illustrate various kinds of points, etc. So I'm going to give you a few that will flesh all this out. I mean, you're absolutely right. Nothing works without examples. Examples are more important than theorems. So anyway, so I'm going to define what DWC. I can keep going, I guess.
Can you go back to the slide where you define the distribution R?
Sorry. Where I was defining
Which class does the distribution R come from?
No, so here I was just making the
lambda. What is lambda?
No, I was making them at a level of generality which is more than I need. Simply because it's not much cost to do that. So here all these definitions of n-letter redundancy, single-letter redundancy, and asymptotic per symbol redundancy that I made were made for a model class of probability measures on sequences of symbols.
Yeah. So this is one thing which I not able. So you're dividing by n.
Yeah.
It makes sense only if the alphabet size is sort of constant across all for every.
Yeah.
It could be the case because this thing allows for the short symbols to be of a certain set, the alphabet size to be growing as a function of n. Then division by n doesn't seem to be the right thing.
No. The alphabet is.
So it could be the case at lambda, and it looks at things of size 10, it looks at one particular alphabet. When it begins looking at things of length 11, it shall use a much larger alphabet. So you have to somehow incorporate this growing alphabet also into the division.
Yeah, for me, alphabet for me is just the natural numbers. That is, I see one symbol drawn from an alphabet, and I'm thinking of basically IID models. In this,
So in IID,
no, but even in more generally, when I write lambda, I'm thinking about the symbol itself. The potential alphabet from which the symbols can be drawn at each time is identical at each time. It's just a natural numbers. That's the only context in which I'm discussing. So lambda, this is a gratuitous generality, but it's.
I will prefer P of n to the infinity. This is P of n to the infinity.
Yeah. So the point is that all these definitions are made generally in the literature much more broadly than just for the IID classes. So for instance, an example of this might be Markovian distributions, pairwise Markov distributions over symbols or sequence of matter, or kth order Markov distribution. Or you might have some renewal model. That's basically the idea. But the general framework is that the viewpoint is that every single time you get a symbol called x sub I at time I, and it's always drawn from the natural. So it is that I can make the definitions at very little cost with the lambda instead of a p to the n.
Okay.
That's the only thing. But I mean, all these questions are very natural, but that's not.
This is probably all these sequences are finite sequences.
No, you have to, as you go along,
Yeah.
you see a longer sequence.
So these are probability distributions on infinite sequences or probability distributions on finite.
No, for me, calligraphic P is a probability distribution of the natural numbers,
Yeah.
and the corresponding IID probability measure on infinite sequences is written as P to the infinite. Yeah, but in making these definitions, I was gratuitously more general by allowing myself to deal with an arbitrary subset of probability measures on sequence, Markov, whatever, because you can make these definitions. Maybe I shouldn't have done that. Okay, so now let me define what we mean by dwc plus. So first of all, we have a notion of we introduce a notion of what we call a stopping rule, which is universal for the given model class. So first of all, what is the stopping rule? The stopping rule is just what a probabilist would call a stopping time. It's you sort of watch, you see the symbols coming one by one, and at some point you decide to say, put a stake in the ground and say stop. I mean, stop basically means you spit out one, and once you spit out one, you have to keep on spitting out one. I mean, we don't really stop. You just keep on saying 0, 0, 0, and at some point you decide to say 1, and from that point you keep saying 1. So a stopping rule is a mapping from sequences of natural numbers to 0 and 1. With the property that once you've said 1, if xn is a prefix of x to the n, then you always say 1. Now, stopping rule is said to be universal for the given model class if the property that you eventually say 1 is going to be 1. If you have to eventually stop it, irrespective of what the underlying model is within the model. So, the notion of a universal stopping rule. Now, pick some delta positive and consider some universal stopping rule for the given model class, and consider some Q, which is a probability measure or infinite sequence of natural numbers, which, remember, for us serves as a proxy for the data compression rule. Now, we would say that this stopping rule is delta premature with respect to this way of compressing, that is, with respect to Q, for the given model P in this model class, if at some I, the stopping rule spits out 1. So basically, stopping rule is playing intuitively the role of the guy that tells you that gives you the guarantee that your current way of doing compression is going to give you redundancy at most delta. That's basically the intuition. So if it happens to spit out 1, it's sort of like giving you that guarantee, but it turns out that the per symbol redundancy is less than that. Then you kind of screwed up. So in this case, we would say that this stopping rule is delta premature with respect to Q, meaning when you're using this compression strategy Q for this particular model within the model class. That's the terminology delta premature. And now, what does it mean to say that a model class is weakly compressible? So now we have the other ingredient is some eta, which is playing the role of confidence. Actually, 1 minus eta is playing the role of confidence. So a model class is said to be data-derived weakly compressible. There exists a particular way of doing compression, namely, which is equivalent, as we discussed, to a measure on sequence of natural numbers, with the property that for every delta and every eta, you can find a stopping rule, which is a way of guaranteeing that you're doing well, which is universal for the entire model class, and such that for every model in the model class, the probability that the stopping time is delta premature with respect to that model for this way of compressing is less than eta. That is, you have to guarantee that you are doing well at least with probability 1 minus eta, where well is defined by delta, and that's true for every delta and eta. For some stopping rule, given the delta and eta, for some stopping rules, you can do that for this specific Q. So this, I mean, a lot of quantifiers, but yes. So this is our definition of what it means for the entire model class to be data-derived.
So here there is no bound on the expectation of stopping time at all. So in the sense that for different keys, this tau could trigger at very different times.
No, the whole point is that tau is data-derived. That's the tau is just looking at the sequence of symbols. It has no knowledge of P.
But we so in this definition so far you're not even talking about how long it will take. It's just that it will eventually because it's universal.
No, the point is you're getting the guarantee that the moment, the point is that you sort of see the symbols. At some point, you have no knowledge of P.
Yeah.
And but you decide that you want this delta eta guarantee, and you decide you're working with Q. So the point is that at the point at which the cow spits out 1,
Yes.
you know that irrespective of what the P is doing, the chance that you're screwing up the delta is at most. Yeah. So it's basically completely data-derived guarantee without needing to know anything about the underlying. That's the whole point of the philosophy. So this is what we mean by data-derived weakly compressible model class. So now I can sort of informally state what we proved. So we have a characterization of which model classes are DWC. And it turns out that the characterization is a local version of the property that characterizes which classes are strongly compressible. This is roughly speaking true also in the insurance story, and there's some general feeling that we have that it's always going to be roughly true. So what I mean by locally is that they strongly, whatever estimation problem might be interested in, classes that are strongly amenable to solving their estimation problem, if they're characterized in a certain way at a global level, then the classes that are data derived for that particular estimation problem will be characterized by the same property, the local level, in the sense that that property we need to hold for arbitrarily small epsilon neighborhoods around each model within the model class. Anyway, when I describe what this actually
They are asked for renovation, but they did not renew.
So we were very fortunate to have a fantastic reviewer, and the reviewer actually pointed out that it's possible that this notion of DWC might be connected with some notion of learning the underlying marginals, which I think. Some problem?
I'm not sure, but
Oh, okay.
I don't see the video. Oh.
Okay.
Yes.
Yeah, it's great. Thank you. Yeah, so I was saying we got a very good reviewer, and the reviewer suggested that this notion might be related to, in some formal sense, to essentially learning the underlying margin of the Raul was also actually suggesting, and suggested one direction of the proof and the other direction we figured out. So it turns out that one of our results is that, in fact, the property of DWC is equivalent to the learnability of the marginal distribution in a suitable sense, which I've also formalized. And I also want to say something about this data-derived insurability notion that Prasad and I studied earlier, which also appeared in JMLR in around 2015, so that's very old work. The characterization there was basically local tightness, where tightness is tightness in the sense of probability theory. And one of the results then in this work is that every data-derived weakly compressible class will be data-derived insurable. And you're asking for examples, for instance, right? So here is a view of the landscape. So if you look at the paper, we provide various different examples that illustrate various points. So the green box here is the set of strongly compressible model classes. The light blue box is the set of data-derived weakly compressible model classes. This big box is the set of weakly compressible model classes. And this rectangle is the set of insurable model classes. So there are, we give some examples of model classes that are strongly compressible, some that are DWC but not strongly compressible, some that are weakly compressible but not DWC, one that, these are sort of artificially constructed to illustrate specific points. So one that falls in this region, one that falls in this region. But in the talk, I can't go through all of these, but I'll go through some of these to illustrate some. So first, let me tell you about the characterization of DWC class. So let's say that, so we have this model class. Remember, for us, a model class is just a collection of probability distributions on the natural numbers. So given a model in the model class, you can define the epsilon radius L1 ball around that model. But we're looking at, remember, we're looking at the intersection of that with the model class. So all the other models in the model class that are within L1 distance epsilon of the given model. So that set is denoted by BP epsilon calligraphic P. So it's not like local around this given model class P. We'll call a model in the model class deceptive if the asymptotic per symbol redundancy of this local L1 ball around that model stays bounded away from 0 as epsilon goes to 0. So that's something bad. It's bad property of that model. So what does that mean in math? So here, remember, we are looking at only models that are within the epsilon L1 epsilon neighborhood of the given model. So we take the soup only over P prime in dP epsilon. And then we look at the corresponding asymptotic per symbol redundancy. So as we saw, we could interchange the inf and the limb soup. So the inf is on the outside, the limb soup is in here, and here is the per letter redundancy proxy, if you like. And then we take the limit of this epsilon goes to 0, but if that thing will still be bounded away from 0, then this little p is considered bad. This is sort of like the thing that strongly compressible basically required vanishing asymptotic per symbol redundancy at the global level. So our theorem essentially boils down to this: is that model class is data-derived weakly compressible if and only if it does not contain any deceptive distributions. So it's a local version of the strong. That's the theorem. I'll sketch a proof of this. I mean, to some extent, yeah, no, we're doing on time. So let me discuss a few examples. In terms of that previous picture, for instance, so here's this landscape picture. So I'm discussing M infinity. So that's a model class that is weakly compressible but not dWc, and that is that's a model class of monotone probability distribution. So probability distribution natural numbers would be called monotone if the probabilities are non-increasing. And it's well known in the literature on compressibility that a model class of this sort is weakly compressible if and only if you can find a probability distribution of the natural numbers, so that for all models of finite entropy we have this property. I don't think I can prove this here in real time. It builds on some results of Kiefer and so on. But this is enough to establish that this class of monotone probability distributions is weakly compressible. Because what you can first observe is that by monotonicity, the properties can be at most 1 over n for the integer n. And so if the model class has finite entropy, then this sum has to be finite. But then you can take Q of n to be this distribution. And so you see that this model class verifies the property. So that's kind of like a proof that it's weakly compressible. It's also not too hard to show that every P in this model class is deceptive. And actually, that also requires some technique. So I think I just leave that to the reading the paper. But the point somehow is that you can break up the natural numbers into a countably infinite number of subsets of which are a disjoint union of subsets, and you can basically you can sort of put model classes within each subset. And so if any given Q was somehow trying to pick up all, actually no, for this it's different. I think what we do here is we just sort of add a little uniform piece to this monotonely decreasing property, and we can make that uniform piece have a very small amount of property but stick out in a very, very long way further and further out, but still retaining monotonicity. And that gives you sort of things which are with an epsilon neighborhoods for which you cannot really pull things together. So that's sort of roughly the limitation. Details paper, yeah. So
is it important to do all this when the alphabet size is in natural numbers?
Yeah.
With common size alphabet, is
Yeah.
any of them becomes easier? Or?
Yeah, I mean, if you know what the finite alphabets, what the alphabet size is, then of course you have bounds on relative entropy and all that right away.
So does it become significantly easier, or is it before?
I think it's, I mean, might be a non-problem, right? I mean, if you sort of everything is bounded with a fixed finite alphabet, then you know it's there isn't that much room to.
Is large deviation happening?
I don't think. I mean, I'm not sure there's any need for large deviations and so on. I mean, if you just we are so I'm not sure. I mean, I'm not sure I completely internalize your question, but I do think that if you sort of have a prior bound on the alphabet, then verifying a condition like this and so on would be fairly straightforward. I think that's the extent of my answer at this point. Let's see, what was the definition? Yeah. So you're sort of looking at, trying to find a single cube which ends up getting these kinds of relative entropies to be small. But I don't think that if there's a prior bound on the alphabet of P, then it's more or less easy to get that. That's the extent of my answer. But I don't know why you're suggesting large deviations.
No, right. That is the meant that you can actually further absolutely bound it. As data comes in, you should have very high confidence on how close you are to actually figuring out the true distribution compared to the regular distribution.
Yeah.
Does it become hard only because the alphabet size only?
Yeah. So I mean, as I said, that's probably a good way to answer your question also. So in terms of this informal discussion, right, we have an informal discussion of main results. We have established already that the DWC property is equivalent to learnability of the marginal distribution. So I'll formalize that in a minute, and I think at that point we can synchronize on the question. So once I go through a couple of examples, I'll state what I mean by learnability. So this is in terms of the big picture. This is the describing what the paper contains in the green box. Of course, there'll be many classes that are strongly compressible, but this is just the paper gives you a concrete one, and this is basically the monotone distributions for which we have some kind of bound on the second moment of the self-information. So this log of 1 over p of x is the object whose expectation is the entropy. So if you take the expectation of its square, that's like, so the log 1 over p of x is called the self-information. It's a random variable, and the second moment is if it's bounded, then there's much less flexibility in this class of monotone distributions, and that's enough to be able to construct a single compression scheme or measure which is able to, so to speak, capture all the p's of this type. So here's an explicit bound that one can prove, which gives strong compressibility. The typo here should be an H. And last example I want to talk about here in terms of this picture is illustrating the other main comment I made, which is that there are DWC classes that are not strongly compressible. So this illustrates that there are weakly compressible classes that are not DWC. This was an example of strongly compressible classes. This is U infinity is the class that illustrates DWC classes that are not weakly compressible. So U is the class of probability distributions that are uniform over some finite range of natural numbers, not necessarily starting at 0, but some finite range. So to see that this class is DWC is kind of trivial, because if you make the epsilon small enough for any given model within the model class, it becomes the only member in the model class. L1 neighborhood around the fixed uniform distribution. And it turns out you can show that the single letter redundancy of this class is infinite. And so the n-letter redundancy would be infinite because the n-letter redundancy is increased with n. And then the asymptotic post-symbol redundancy would also be infinite. So in fact, this is not strongly compressible. So these are some examples. I hope that's reasonable. There are many more examples in the paper. Some of them require artificial construction. So now to get to Rahul's question, this is a definition of learnability. And it's a kind of natural definitions. As you go along, what you do is you attempt to try to learn the marginal. So formally an estimator is a mapping from sequences of symbols, that is observations, to probability distribution of natural numbers. And we would say that a model class is learnable if for every delta and eta, you will be able to come up with a stopping rule, which is universal for the model class, such that irrespective of which model is under effect in that model class, so this stopping time is playing the role of the time at which you say my estimate is good enough. So at that time, your estimate, if it happens to be not good enough as measured by delta with probability bigger than 1 minus eta, you're in trouble. So the probability that it actually satisfies, it doesn't screw up. So this dpq is less than equal to delta is at least 1 minus eta.
So there should be something about also considering the value of I above, because by definition of the stopping rule, so you can just take I very large and then you should get the correct value of the peer average anyway. Because once it hits, it always hit. So
Sorry, for
right now there is this I greater than 1, so that the line has hit and the estimate is good.
yeah.
But eventually the estimate will become good.
Yeah, but the point is that we would say that the model class is learnable if you can actually come up with these stopping times. So we have we have to not only this is eventually going to, we have to tell you that at this time we have to tell you that it's at least that it's good.
This is the first I. So this should be the smallest I for which this is 1. Already the estimate is good. That's what we wanted. So the smallest I when the time hits, the estimate is good. That's what.
No, so the way you want to think about it, is there a time at which I'm being given the guarantee that it's good, but it's not good? I mean, this if the DPQ is high, then it's not good. So basically asking, is there a time at which this thing, is this thing is telling me that it's good, but it's not good, and the chance of that happening is small. So and I think when you have a finite alphabet, you can imagine that you come up with schemes like this, right? So I think that's basically quite close a little bit here. Although I must say, we didn't really think concretely very much about finite alphabet specifically because it's not very I mean, not for the flat kinds of things. Again, I mean, many of the estimation problem people are interested in have got much more interesting alphabets, like Euclidean alphabets or Cohen space alphabets and so on, right? So, at least accountability is sort of like as easy as you can make it. So this is pretty much this scope of the results and so on. So now what I'd like to do is maybe, since I have a few minutes, just get some sense of the proofs. So the proof of necessity is rather straightforward. So I'm discussing the local characterization of dwc. So necessity basically means that in order to be dwc, it must be the case that no model in the model class is deceptive. So now suppose you have a model in the model class that is deceptive. Then we basically have to come up with an argument to say that that for some delta and eta we cannot sort of find any stopping time which is going to give us the delta eta guarantee for some other model within the model class. So the argument is basically look at pick some stopping time which you think is going to work for you. Since it has to eventually stop, that is part of the definition of universality. For every n, you can look at those sequences on which the thing stops, and as n increases, this probability of this under the p that is deceptive, or any p for that matter within the model class, will have to be non-decreasing and eventually go to 1. So now what you do is you basically observe that if you have other p tildes in the model class that are very, very close to this p which you know exists and is deceptive, then those p tildes will also be giving this set a reasonably high probability. You have to go, I mean, here our epsilon is very, very small, so we can basically ensure that these p tildes also will stop essentially on this particular set for which the p stops. But the p is deceptive, so somehow you've got this the bounded redundancy. So eventually, however small epsilon is, you start staying away from delta. So now this p tilde is somehow going to have that problem with respect to the q because it's very close to p. But it's stopping, right? So that's sort of the idea. I mean, you have to go through the details to really understand it. But this is sort of the nature of the necessity proof. It's rather easy. What's really interesting is the sufficiency proof. And then I find it easier in terms of the talk to describe the way it looked in the insurability document because it's much cleaner there. And the proof in this document is a version of that. So let me just tell you what the insurability work was about. We call it insurability because we were thinking about some guy who is trying to write a contract for covering for losses. So this person, let's say it's a bank or an insurer or something, just watches if some losses provided, and at some point it writes a contract. And the goal of this person writing a contract is to charge premiums in such a way that the loss is always below the built up capital. But from a probabilistic point of view, that's sort of equivalent to a tail domination problem. So it's like you're seeing a sequence of our losses for our national numbers. So you're seeing a sequence of losses, and after a certain point, you have to be sure that you're able to come up with an estimate for a number which is going to dominate the next loss. In the insurance, it's not the number itself that is serving the role of the premium because you might have built up some capital, right? So you can recorrect and charge a premium by using your previous capital. That's something you already have. So basically what we call insurability is equal to tail domination. So think of this as a tail domination problem. So tail domination strategy is a sequence of functions from sequences of natural numbers of length n, say, to natural numbers, which is supposed to have the property that somehow by estimating based on what natural numbers you've seen so far, you would come up with an estimate of something that is pretty good chance of being higher than the next natural number you use. So our definition in that earlier work from 2015 of a model class of probability distribution of natural numbers to be data-derived weak insurable was as follows. For every eta, we should be able to come up with a tail domination strategy and a stopping rule that is universal for this model class. So this stopping rule in this discussion serves the role of the point at which the insurer is sufficiently confident after having seen the losses so far to write a contract to the guy who needs to be contracted. And from that point onwards, the chance that the insurer goes bankrupt, that is somehow fails to dominate the event, that chance should be small. So this is the definition of what it means for model class to be data-derived nature. Now, the way we did the proof here, we proved here our characterization was that model class data-derived insurable if and only if. Again, we use the word deceptive, but now deceptive means now a model would be called deceptive is if every L1 neighborhood of it is not tight. So tightness is this idea that you'll be able to find for any given delta a place large enough that uniformly makes the tail property beyond that place to be less than delta. So a model is not tight if in a particular neighborhood of it, if the supremum over all models in that same neighborhood, if you look at the delta, where the delta percentile hits, that isn't bounded. So this was the notion of data-derived insurability. I only have a couple of slides left, but I want to get to the main point. So the main point, technically, in the sufficiency proof, which is much more interesting, was to use a symmetrized version of the relative entropy, which is well known in information theory. It's called the Jensen-Shannon divergence between two probability distributions. So you look at the divergence between P and the average of P and Q, and plus Q and the average between P and Q. The Jensen-Shannon divergence has very nice properties, which are worth knowing if you want to use it for something else. First of all, the topology it defines is identical to the L1 topology because of these bounds. But far more interesting is this mysterious inequality, which is sort of like a pseudo triangle inequality. So relative entropy has this big problem that it doesn't satisfy the triangle inequality. But the Jensen-Shannon divergence ends up satisfying a property that morally is like a triangle inequality. So it's not true that JPR is smaller than JPQ plus JPQR, but JPR squared times the constant is smaller than that. So morally, this serves as a triangle inequality. And that's the technical heart of the sufficiency proof. And that is illustrated in the next two slides. So you're trying to come up with a way to come up with this delta eta stopping times. So essentially what's going on is you're seeing this data as you go along, say in the insurability problem, also in the compression problem that we talked about. But let's focus on the insurance problem. So you just want to decide whether your belief about what the marginal distribution is based on the data so far is good enough for you to achieve the objective that you want to achieve, which is either insurance or compression or whatever. So what you do in the insurance problem is you define for each model in the model class, which now you know, your assumption is that there are no deceptive distributions. So there will be some L1 ball around this model where all the models within that L1 ball of this given model have a uniform bound on their tail, right? Because they're tight. So for any given delta. So you call that radius the reach of this particular model. Now, you can then build such balls around each of the models in the model class. And because L1 is Lindelof, you know that there is a countable collection of these sets which covers L1. Now here you're observing the data. As you go along, you look at the empirical distribution, and it's going to eventually happen. This empirical distribution actually need not be the model class, but eventually it's going to happen that they're going to fall within the reach, just in terms of L1 neighborhood of one of these reaches, right? Because they cover all of them. Now your decision is, do I accept this? Do I believe that the center of that reach of that ball is good enough for me to pretend that it's actually driving the data? That's the heart of the matter. Okay. So So essentially what you're doing as you go along, you compute the time, and this will eventually enter the union of the countable collection of reaches coming from the end of property. The decision that needs to be made is whether to allow oneself to be tracked by this particular L1 ball or not. Now here is what's going on. So let's say that your true distribution is P. You don't know that, all you know is the data. You've seen the empirical distribution bopping along, and at some point it falls within the reach of P prime. So you're now faced with the following dilemma. It may be the case that the empirical distribution falls within the reach of P prime, that is this ball, but the P itself may be outside the reach. The P is outside the reach, you're sort of loosely speaking screwed, right? That's the idea. So you've got to figure out how to handle this, and that's where that triangle inequality does the trick. So this picture here is completely the heart of the sufficiency proof. The idea is that here is the P prime that is the center of the reach. This is your empirical distribution. If your empirical distribution is close to the center of the ball that is what we call the reach, and you're still in bad shape because the true distribution is far away from P prime, it will automatically be the case that the empirical distribution is far away from P. So the probability of that happening is small. Because of that sort of pseudo triangle inequality, you're able to control the probability of bad things happening. So this is how things work in the insurance proof, and pretty much exactly how it works in the data-derived weakly compression proof, which is the latest paper, except that you have to define reaches and all that much more carefully technically. So now the reach is not so much defined just by type, it's not defined by tightness, but it's defined by this local vanishing asymptotic redundancy property. So for any given model in the model class, assuming that it's not deceptive, you know that there exists some proxy for the compression scheme, such that for all delta there exists some epsilon, so that in that epsilon ball around that P, every P prime will be it will be good enough to use this particular Q to compress for that P prime. That's sort of the idea. So you define the reach according to this epsilon P delta, and then you use pretty much the same kind of mechanics to figure out how to decide when to accept the so-called center of the reach as being good enough for you to compress according to that. And that's pretty much the whole story. So, but again, as I said in the beginning, and I'd like to really emphasize, you may not, many of you probably don't care about compression, but this is a philosophical viewpoint that I think it's worth thinking about. If you care about that, also who knows what everybody cares about. But point is, the data-driven viewpoint is in principle applicable to interpolated all compression as a non-parametric estimation type problem spaces between what people have traditionally been doing, which is either uniformity or pointwise, by introducing these stopping times and all this sort of business. And we also seem to have generally believed that the general principle at work seems to be that whether model class is data derived universal or not is a local version of whether it's strongly universal. That is just a, it's not a justified statement. We're looking at a few other things on and off as a very slow time scale. This paper could actually have been written 4 years earlier, but that was not putting it all together. So thank you very much. Everything that we've done assumes IID in terms of the mechanics of the proofs and all that. But I think in principle, it should be possible to go beyond that. How much? We certainly Markov and all that. I don't think should necessarily be a big issue. But we haven't really thought about that in any serious sense. So whenever you try to do something, you find things that you unexpected. Just a few aspects. I don't know what to do. I know that Prasad is thinking about various kinds of Markovian problems, but they're not really along these lines. So we might have the best insight into that. But I think it should work more generally.
In statistical analysis series, there is Rademacher complexity.
Yeah,
Which I talked about in the context of data driven.
Yeah.
Is there any analogy between those two?
So I gave an entire talk in 2020. I can share the slides with you, where I claimed a version of this theory for that whole story connected with Bartlett's work and Rademacher complexities and all that. I have the slides on it, but I've never written up the papers, so they may all be wrong. But I can share them with you. Yeah. Sure. Yeah, but yeah, it's a natural next thing to do. So I went through all that literature and tried to figure out how this might work.
how this is, so is there some coming up with this algorithmic description of this time? So,
I mean, it just boils down to making the definitions in a way that involve these stopping times.
Since right now it seems that to check whether you should strike, you need to compute the yield level with P, which you don't know.
Yeah.
So,
I don't know when the college this work or what?
No,
The college this work. Yeah. So what was the question?
This tau is like
Yeah.
thing you define in terms of there being a tau.
Yeah.
But if I want to actually given the construct this, so if
Yeah.
I'm actually running this.
Yeah. So that's what the sufficiency proof tells you how you might do that. So the way you construct the tau is you know for any given delta you have all these reaches. So you cover the space with the set of reaches, and the way you construct the tau is you just keep bopping along and you ask yourself, do I allow myself to get trapped by this reach? And we have some rules that allow you that describe that. I mean, you have to of course give something concrete, which I did mention in this talk, and that's what we have done. So essentially, concrete way of defining every tau.